Good morning, ladies and gentlemen. We're Team 3DSolar. My name is Carl Jai. These are my team members, Mohammed Arif and Christian Bernard. Our advisor is Dr. Bilal El-Zahab, and our project is a three-dimensional solar panel. Now for a quick introduction. Solar cell research and development has been around for many years, even since the early 1800s. But in recent times, they have become more popular as a means of primary energy generation. Now, a solar cell, which is also known as a photovoltaic cell, and the idea behind this is to convert sunlight into electricity. Solar cells can be electrically connected together to form a module, as seen here in the picture. And a module can be also wired together to form an array. This will yield the maximum amount of energy. Now, for our problem statement, we want to address pollution by reducing overall carbon footprint. But I'm doing this by implementing our three-dimensional geometry to increase energy generation so that in the future we may see more photovoltaic plants rather than the polluting fossil fuel ones. For our motivation for this project is fairly simple. Reducing the dependence on fossil fuels is at the top of our list. Now, as we know, the demand for usable energy is increasing on a daily basis, and fossil fuels such as coal and maybe gas will become scarce, and it is for this reason that we plan on harvesting as much energy from the sun as possible, for the sun is an unlimited energy source. Now, our solar panel will be designed in such a way that it is portable enough to reach remote areas that are basically off the electrical grid.
Alright, so for our objective, we plan to maximize sunlight absorption by using a 3D geometry that the sunlight will be perpendicular to the panel at all times to maximize efficiency and absorption. We also plan to increase energy storage to effectively utilize the renewable energy by making use of the sun's unlimited resource and adapt the solar panel for potential application in residential areas by making it portable and convenient.
As the world's demand for power increases, demand for fossil fuel to create the energy also increases. As Carl mentioned, the fossil fuel accounts for much of the CO2 in our atmosphere. So sun is the only source of clean energy, which is an unlimited source of energy. It is the fastest source of energy in the world right now. Most of the countries are shifting towards the energy, cleaner energy. For example, Germany's plan to reach 30% of its energy by 2020 from its renewable energy. In contrast, US only produced 1% of its energy from solar energy. In 2005, it was a $38 billion industry and growing at 10% a year. It is true for 2 billion people in developing countries who have no access to the grid. And it is creating more and more educational and economical development in developing countries. Our design, we are planning to design a such shape which is cost efficient and easy to manufacture. And we're considering two different materials in our design, polycrystalline and monocrystalline. Polycrystalline is cheaper, but it's less efficient. Monocrystalline is efficient, but it's expensive because it's pure form of silicon. These are the two shapes we are considering. As you can see, the rectangular shape is the conventional shape we see, which is not as efficient because it only converts 15 to 20% of its energy to electricity. And our goal is to expose the base area to the sun's ray at 90 degrees as much as possible to generate as much energy as we can.
Alright, so the solar panel is made up of photovoltaic cells. This is a photovoltaic cell here. It's made of two silicon layers, a positive and a negative. And how it works, the photons are absorbed from the sunlight and electrons are released. And since silicon is a semiconductor material, it can efficiently transfer the flow of electrons, which is then captured by the electric circuit that connects the two layers. And once the electric circuit captures the electrons, it moves to the charge controller, which regulates the output voltage to the battery, so not to overcharge the battery and damage it. The battery is where we store our energy, and DC power can be used from the battery, but since most appliances are AC power or 120 volts, we use the inverter to convert the low voltage to AC power. This is our cost analysis. As we can tell, the power inverter is most of the cost, which is about $1,100. So our estimated cost is about $2,000.
Now, as far as our timeline goes, for the fall semester, for this semester, this is what we mostly worked on, and for the upcoming spring semester, this is what we're planning on working on. This might change. It is not set in stone, so this is what it is for now. And these are some of our references, and that is our presentation. Thank you.
So I saw your design. You have a couple different structures. One's a cube, one's a pyramid, right? So we're in the northern hemisphere, so always the sun is in the southern sky,
From the south,
right?
yes.
So why did you come up with two designs that have four sides to them that probably wouldn't be? One side would mostly be in the shade at all times.
Yeah. Well, why we chose this is because what we plan on doing once we have assembled and built our three-dimensional solar panel, we want to implement reflectors so that the sides that are not exposed to the direct sunlight, some sunlight will be bounced back. So we want to reflect it with some mirrors and put it back on the sides that are not exposed to sunlight.
Yeah, so we want to capture this stray sunlight to maximize absorption.
Okay. So what's wrong with just making a panel that faces south and not having to do that?
Well, if you use a conventional panel, like the basic shape that we all know,
Uh-huh.
the rectangular one, if you just face it south, what will happen is that the sun is a moving source.
Sure.
So for that panel, you would need a what they call a solar tracker to mount it on, and every solar hour of the day, you would need to move it to capture the most amount of sunlight.
And you wouldn't have to do that with the mirror?
With our design, we would make it a standalone device, meaning it would be designed in the absence of a solar tracker. So even though one side would be exposed, with the help of reflectors, we can expose all of the sides that are to sunlight.
Okay. Don't you have to move the reflectors though if the sun is moving?
No.
You don't have
Well,
to
the
move
reflectors will be all around the panel, so any direction the sun comes from, we should be able to capture it
Yes.
as much as possible.
Even though the full panel that is not, let's say, in the shade, will not capture all the sunlight, it will get some. So we hope by then, increasing the energy.
So are you doing a study to say exactly, sorry if I'm taking everyone's question. Are you going to do a study to determine which is more efficient? I mean, almost everyone out there now uses just south-facing panels.
Depending on.
Sure, so are you going to compare your results with
Of course,
a south-facing
yeah, we're
panel?
gonna test using our design and also a basic rectangular shape
Compare them.
and compare the results we get just to prove our efficiency is greater.
But didn't you say that you're building this for use anywhere in the world?
Yes,
Yeah.
it will be
So it can,
applicable
it
anywhere.
doesn't have to be just south
No,
facing?
no.
But if you're in the southern hemisphere, it would be in the summer.
Yeah, but if for a
Right,
specific
yeah,
purpose,
right.
then yes. Yeah.
Okay, the question I ask right off the bat is, why did you select the geometries you selected? Because I can right off think of a couple that would actually be
Yeah,
more
the-
effective and more efficient.
True, there are many more. You can come up with hundreds of different geometries to come up with, to select from. But we chose these because they will be convenient for us to calculate the surface area to compare it to the regular rectangular one. We were also thinking about a dome shape. There are many different shapes, odd shapes, non-conventional shapes, but it will be a lot difficult for us to calculate the area and to compare it to the regular rectangular one.
Also, if we use a dome shape, we'll
Now remember what your project objective is. I mean, you state here to design and construct a three-dimensional solar panel to maximize absorption of sunlight and maximum efficiency. So you're going to need to come back to us and prove to us that your design meets that
Yes, of course.
project objective. Okay, and is this design going to meet the maximum absorption of sunlight, maximum efficiency?
As of when we actually test the panel and compare it to the basic shape, and we see that the output of ours is like we're trying to shoot for at least double of what the rectangular can give us, then we would say it is very successful.
This is an initial design. This is the first design we'll do our testing on. So it will change as we go along to come up with the best geometry possible. It's more of a trial and error process. So whichever shape can match or has a better efficiency, that'll be our final design. But as of now, this is initial design.
Okay.
Did you estimate the lifetime of the panel?
Well, the materials that we're using are going to be mostly, the solar cells are off the shelf, and they have an expectancy of about anywhere from 20 to 30 years, and they only decrease in efficiency about 1% a year, so it has a pretty long life.
You said, at least in the little report that you have here, that you believe that this project is going to have a positive impact on the environment and the society. Can you talk a little bit more about that?
Well, of course. I mean, once this design proves to be effective and we can produce more clean energy than what these the basic rectangular shaped one gives us, we can, in the future, we can see more photovoltaic plants maybe using this type of design, a three-dimensional design, to produce more energy. As we know, the demand of energy is constantly increased. So we can hopefully get rid of these polluting fossil fuel ones, create a better environment for everybody to live in for the future.
Can you talk a little bit about scalability? So you're saying that plants are going to use this specific design. To me, if you have a 3D shape, right, you can't scale that up to become a huge solar farm.
That's why we are,
like
in
that,
our design,
right?
that's why we say we're going to try to adapt it to residential needs because, as you said, most photovoltaic plants are just like a huge rectangle or solar cells, and that'll be much easier for them to use than our design. So that's why we're trying to focus more on residential needs, appliances.
As research evolves and people keep doing research on solar cells, others might see our idea and come up with another way to implement this for a much bigger scale.
What about the costs? If you could do it for residential, I mean, what would be the cost for the residents? I mean, have you thought about it?
For our panel, but as of specifics, we're not there yet. We have estimated a cost of about $2,000, but this is with all apparatus, including inverter, batteries, charge controllers.
So how much energy would that give you in terms of savings, right? So it's gonna cost $2,000 in 1 year. How much money will that save a person?
Well,
That would depend on the output that we get. That we have to test that first, and then.
So that
we
could
can
be
get back.
something very important.
Yes.
Yeah. Any other questions? Yeah.
Just to summarize the questions back and forth,
Yeah.
in order to determine marketability of your product, at what point in your cycle do you compare your selected geometry and its savings and cost versus what's on the market to assume that you've got a product that's viable?
you mean compared to the basic solar panel?
Yes, if I'm going to buy it for my house, why would I spend $2,000 on yours to get X amount of savings versus 100 from that?
Well, when we run our tests, we're going to compare the results with a rectangular panel and our design to prove efficiency. And the efficiency is supposed to be around double because the efficiency of the rectangular panel is around 20%, and we are projecting our efficiency will be about 40%.
And also, if you were to buy a basic shaped panel, like the rectangular one, the panel itself is not that expensive, but you would have to purchase a solar tracker for the panel, which is the bulk of the money, which is usually not shown once you buy the panel.
Can I do one more? Just where'd you get the 40%? Sorry. Where'd you get the 40% efficiency rate?
Well, so far doing our research with our advisor and previous test run, there was a guy in MIT who did a similar experiment, and
And so what was his shape?
He had a parallelepiped shape,
Yeah.
and he made some sort of tower. It was
Like a tower.
An odd-shaped
Okay.
tower, sort of.
And that increased the generation from factor of 2 to 4, actually 2 to 20 actually.
Yes.
Quick comment. It's important in your cost-benefit analysis that you compare, you were saying about the solid track with the basic shape.
Yes.
Obviously, on your potential shape, you may have 4 times more area than the basic shape. So taking into account solar panels are expensive devices. It's important you compare the basic shape with the solar tracker versus
Yes.
the potential shapes only. And there, you will have a very good estimation of which one is the best solution.
Of course. But even though, like, what we've done in our research, even though our solar panel, if our solar panel would cost a little bit more than the regular rectangular shape, but if we're able to produce more energy,
That's what I'm saying.
It will
It's a
work.
cost-benefit analysis.
yes, of course.
Can I ask one question?
Uh,
One question I've heard about solar panels from other people is that this hurricane issue down here in South Florida, and that being attached to the house and insurance issues. I'm thinking in 3D shape, is there an issue with wind? with these being on a roof.
I hope that's a test.
Let me go find out.
Is that a test?
It's not a test.